I'm happy to be here. And yes, I'll be talking about wavelet representation for smooth Calderon-Zygmund operators. And so we'll start off just talking about wavelets for a little while and then get to the Calderon-Zygmund theory by the end. So the wavelets, from a group theory perspective, they are an action of the affine group, or the upper half space, which we will denote by ZD for the Euclidean space across the axis 0 to infinity. And this acts on any function by translation and by dilation. So we'll use this interchangeably, Z and WT. So W is the translation parameter and T is the scale, or the dilation. And we normalize to be, we have L1 normalization. And so this is what we mean by a wavelet. We take a function and we apply this action to it on the entire upper half space. And the special functions that will be most helpful for us are ones that are admissible. So a wavelet function is admissible if its Fourier transform satisfies this admissibility condition. So you look at a direction and you look at the Fourier transform in that direction, and you integrate from 0 to infinity with respect to this measure. And we'll usually just pick phi to be radial, so we don't have to even worry about this, directional thing. And then we just have to basically normalize. So many functions is the point satisfy this admissibility condition. And if a wavelet is admissible, we have the Calderon formula, or the Calderon reproducing formula, which says we can write our function as a superposition of these rank 1 projections. So we project onto the wavelet, that gives us the coefficient, and then this is our column vector. So then the measure associated to both this group and to the formula is the same one. It's this Haar measure. So from this perspective, the wavelets are what's called a continuous Parseval frame, which is a generalization of an orthonormal basis, and it's highly overdetermined. We have this representation. So we're going to represent our functions this way, then apply the operators, and that's going to give us our representation theory for the operator. Pretty predictable from that perspective. And then the smoothness comes in. So the admissibility condition implies that phi hat must vanish at 0, right, due to the singularity of the measure. So with that in mind, we actually want more from our wavelets than to be mean 0. So we want additional cancellation. So we'll use this notation of Schwartz functions, which have vanishing moments up to j, right? So alpha equals 0, that's just the mean 0 condition, but we require vanishing moments up to some certain level j. All right, so that's some technical stuff for the setup. And for us, we're going to actually look at functions that are not wavelets themselves, but behave like wavelets in their scale and decay. So we have this Holder type norm that we introduce, the star norm. So it measures the decay of the function, and then that it has some sort of Holder continuity, again with the decay. And using this norm, we define the wavelet class. So these are things that are not wavelets themselves. They don't satisfy the Calderon formula, but they are close enough. So they behave like wavelets according to this norm. So what does this say? We take our function, we take a derivative of it, then we move it back to where to z. So it's like our wavelet is localized to z. So we move it back to the origin, and then we apply the norm. And this is just a scaling term. So to understand where all of this is coming from, and then we have a cancellative subclass. And to understand where all this is coming from, just take one wavelet and we can see where all these norms and everything are coming into play. So if we take one wavelet, then we act on it by the translation and dilation, then it will belong to this class. Let's check. So when we differentiate it, we receive power t to the minus gamma just from chain rule. And then if our function is Schwartz, this is just automatic that we can get some decay here. So, then if we move this back, if we translate back, then I'm missing actually a t to the minus d everywhere. My bad. So there's also t to minus d, t to the minus d. Okay. So then we translate back, we'll be satisfying this portion of the norm. And then there would also be a corresponding Holder estimate. So this is just a generalization of this bound for the wavelets, and then a similar one for their continuity up to some delta. Okay, so morally, things in this class psi are wavelets for all of our purposes. And that's going to be the idea is that the Calderon-Zygmund operators, they will map true wavelets into these wavelets, into these approximate wavelets. And that's going to be the key idea, which is not original to us. I mean, there's always been this atoms to molecules sort of correspondence, which is very similar to this. And that's going to yield our representation more or less. So with the reason we introduce the wavelets in the wavelet class is to introduce our intrinsic operators, which will be a wavelet form. So we take an approximate wavelet, nu, and we take a real wavelet, phi. With these two things, we define the wavelet form. So we take the coefficient on F, the coefficient on G. This gives us a wavelet form. And you can check the kernel of this form. It's we take the tensor product and we integrate along the parameter z. That'll be the kernel of our operator, and it's not too difficult to check that this kernel is a singular integral kernel, and even with some smoothness. So we take the derivative, we get an extra bit of decay. So not too difficult to check this computation. I won't spend any time on it for the sake of time, but to give you more insight about the wavelet form, we will take a second. So if nu z, if this was a true wavelet, the translation and dilation of one function, then the wavelet form would basically be a pointwise product of the square functions. So I've written down the computation here, just to Cauchy-Schwarz inequality gives you ZD integral over ZD is integral over RD and then integral from 0 to infinity. So so we just apply the Cauchy-Schwarz. This gives us one square function. This gives us the other square function. If these were really wavelets, if this was another phi z, but they're approximate wavelets, so we can't appeal. We don't have as good of estimates as we do for a square function, but we still get enough. And we call such a function an intrinsic square function. We actually take the supremum over all of these members of the wavelet class. That gives us an intrinsic square function. And that's what we'll ask you. So you should think of the wavelet form like two square functions, the dual pairing of two square functions. So so the wavelet forms, they satisfied this estimate on their kernel. And I said this was a singular integral kernel. So let's just briefly give the definition of what we mean by a smooth singular integral kernel. So, and we'll even talk about the multilinear setting. So our theory here is actually going to get to the multilinear case eventually. So we'll just start off with the multilinear definition. So singular integral satisfies the smoothness and the size estimates. And we even require that it satisfy it up to some derivatives. So as we take a derivative to the order kappa, then we get the extra decay of order kappa. And we can go all the way up to our total order of k. So that's what it means to be a k delta singular integral. And then we can have a singular integral form, which will be the product of all of these integrated against a kernel. And we'll interchangeably go between the form and the operator. So sometimes I'll write lambda where I should write t, or but there will be some abusive notation, but lambda is the form, t is the operator. And this is what it means to be associated to a singular integral kernel, in which case we have a singular integral form, or t being a singular integral operator. And in general, I mean, just looking at the square function example from the previous case, being probably everyone here knows, being a singular integral is not enough to be bounded. You need to have cancellation, which the square functions have a whole lot of. So as a rule, singular integrals are not bounded unless they have cancellation. And then how much cancellation? Of course, this is the famous T of 1 theorem. It tells us when a singular integral is bounded on LP. We need to have boundedness along the diagonal, the weak boundedness, and then we also need to satisfy the testing type condition, T of 1, and also the adjoints, and this is in the multilinear setting as well. And I've written here LP and LPI, so always LP and PI will be Holder conjugates, some Holder tuple. So I'm not going to write that 1,000 times. We just always assume that these PIs satisfy the Holder conditions, and the PIs they always have to be between 1 and infinity. So then that tells you about P. Well, actually, PIs they can be infinity, just not all of them can be infinity. Okay, so that's just some technical things, but yeah, the point is that I'm trying to get at singular integrals. We need to have a testing condition to know if they're bounded, and that testing condition should tell us something about the cancellation. So, okay, so let's discuss now. So, yeah, let's discuss now what happens in the Sobolev space. So that's the point of this, the smooth singular integrals. So this is just for rough. These are for regular singular integrals that may not have any smoothness k. These are the classical case is for is not looking at Sobolev spaces. So we need to define Sobolev spaces as follows. So there are two types of Sobolev spaces. There is what's called an inhomogeneous, and then this is of course called the homogeneous, and that comes from the fact that it's homogeneous with respect to like certain dilations, right? This will be because all the derivatives are the same order. This will not be because the derivatives are all orders. Okay, so these are our definitions for the Sobolev space, and if we want a singular integral operator to be bounded on the homogeneous Sobolev spaces, then actually you can find out that it has to satisfy this condition. So testing on polynomials and then taking the derivative, it must be in BMO at the highest order. And then if you test on any lower order polynomials, it actually must vanish, which is maybe the surprising part, that you have to vanish for the lower orders. And so that's actually kind of a restrictive condition, in order to be bounded on the homogeneous spaces. But it's actually necessary. I mean, we're actually showing right here that it's necessary. So under these conditions, there is a linear representation theorem proved by DePlinio, Wick, and a graduate student at WashU, Tyler Williams. And this is what our work is based on, that I'm doing in extending this to different settings. And yeah, they've proved basically under this same condition P that you have a representation as a wavelet form plus some paraproducts, which I'll talk about later. And the consequence of this is the sharp AP weight estimate for the homogeneous Sobolev spaces. So for these, and this shows, that you can do no better than this assumption if you restrict yourself to the homogeneous cases. All right, so now let's talk about the bilinear case, or we're going to now go to the multilinear case, and there some real changes have to occur because, well, we'll see. There's some real differences, and really we can go to all the multilinear cases, but we'll just do bilinear to be concise. So we have a similar necessary condition that we can check. So if you preserve the homogeneous Sobolev spaces, then again, you have to be in BMO at the highest order when you're testing on polynomials of the highest order. And then everywhere else, you have to be 0. And I said that this was a restrictive condition for the linear case, and it is, but it's a really restrictive condition in the bilinear case. Okay, so the classical bilinear operator is the pointwise product. So the pointwise product only maps the WIP cross WJP into the minimum of I and J. And so it cannot, so it's not going to obey C, and moreover, it's not ever going to preserve the homogeneous spaces, right? This term over here is not in any homogeneous Sobolev space. It's only in the inhomogeneous ones. So the bilinear operators, unless you're going to study very special ones, which satisfy this type of condition, which not even the product satisfies, then we're going to have to go to inhomogeneous Sobolev spaces, in which case these restrictive conditions are not going to hold, and so we're going to have to come up with different kinds of testing conditions. So the idea is to find testing conditions for the multilinear operators, and those testing conditions cannot be P2 anymore. For what we just said, this only holds if you're preserving the homogeneous spaces, which in general the multilinear operators cannot do. Now, if you know anything about multilinear operators and smoothness, then you know the solution to this problem is to break up your the identity or the Leibniz rule. You break it up into 2 pieces. One, and each of those pieces do obey this property, but kind of in a flip way, right? And the way that comes about is through what's called a para-product. And so, of course, we're going to deal with this same problem using para-products. So a para-product, the way we're going to create para-products is as follows. So we take what we call a gamma family, which maybe I should skip some of these technicalities because it's not so important. The idea is the form looks like this, where these are gamma families. So the point of a gamma family is it only turns on when you plug in the correct polynomial here. So when you plug in x to the gamma, you get 1, and everywhere, or you get a multiple of 1, and every time else you get 0. So the para-product only turns on when you plug in the correct powers of x to the gamma into both of these slots. And in that case, by the Calderon formula, all of this cancels out, and you just get that when you plug in the x and y to the appropriate powers, you get the symbol B. Okay, so these are the para-products that we introduce, and they do preserve the Sobolev spaces. However, the target space can be pretty bad. It only goes up to gamma. So we have to actually assume more regularity on B. And if djb, the derivative is in BMO, then we can bump this space up. Okay, so I'm out of time, but I've got through all the setup. Let me skip to the theorem. Okay, so a Calderon-Zygmund form, it has para-products. That's the definition. We also have the multilinear wavelet forms, which we already discussed. Okay, so let me get to the theorem, and then I'll be done. So the bilinear representation is that if we have a K1, K2 delta So K1, K2, those are the two different smoothness in each of the variables. Calderon-Zygmund form, then we can find smooth wavelet forms starting at this smoothness going up to the top. And then we have the paraproduct forms as well. So a corollary of this is that we can get the estimates on the inhomogeneous Sobolev spaces here, and even with the AP weights. And actually, we can even get the sharp AP weights, just like in the Lebesgue space theory. And I just want to mention a bunch of results of this type. Well, so how do we do this? We do sparse domination of the wavelet forms after integrating by parts. So the wavelet forms allow us to integrate by parts, and then we do sparse domination. And only recently was sparse domination, the multilinear theory, completed. And when it was completed, they got the sharp exponents. So that's how we get the sharp exponents. And many results of this type have been done by many authors, which I just want to mention. But in many of these cases, it's either unweighted or there's not the full paraproducts assumption. So we tried to kind of complete this and have lots of not assume the cancellation, but add in all the paraproducts. And yeah, so okay, let me stop blabbering on. That's a good place to stop with the statement of the theorem.